Anyway, are you ready? So we have I'm not sure how much we have. We have 30 if I'm not mistaken. Okay, we have 30 and now we have 27. Inshallah they will coming, inshallah. Okay, have you watched the video? No one watched the video. Okay, I will share you the entire screen. So if you hear a few things, call my name, so just ignore. Okay, have you see this? Can you see the shared slide?
Can, Doctor.
Okay, good.
Yes. Yes.
Okay, great. As I said before, if I play the video, for sure will be lag. So better you watch later. So this will increase your awareness to change your mind about the electrical machine. So I believe today we go to the new subtopic, which is the magnetic field. So this subtopic is one of the important parameter or the magnetic field is the most important or the major things in the electrical machine. Okay, so are you ready?
Yes, Doctor.
Okay, it's good.
Yes.
I think let's start. So others, don't worry, I'm recording the video, so later on you can see. So if you want to record the slide, record the video, so no problem. Okay, Bismillahirrahmanirrahim. Good afternoon. Again, today we're going to study about the magnetic field. Okay, we have a few more subtopic before we end the chapter 1. Okay, so as previously stated, magnetic field are the fundamental mechanism. This is a fundamental mechanism by which the energy is converted from one form to another in electrical machine. Okay, either electrical to mechanical or mechanical to electrical. Okay, so there are 4 general principles. Okay, so there are 4 general principles. The first principle is electromagnetic action. Okay, when there is a current, okay, when there is a wire, okay, for example this, or maybe terlalu kecil, okay, current carrying wire, so wire and then the current flow. Okay, so when there is a current flow into the wire, so they will produce a magnetic field around it. Okay, I believe if I still remember that I did the experiment in the in my secondary school, if I'm not mistaken. I believe all of you also the same. Okay, and then the second one is a transformer action, where there is a time changing magnetic field. Okay, induce a voltage in a coil of wire if it pass through that coil. Okay, magnetic field induce, there is a magnetic field induce a voltage. Okay, so this concept using in the transformer action. And also if you can imagine the wireless charger, the wireless charger. Okay, the concept of wireless charger is by using the magnetic field, the coil, and also the current flow. So when there is a current flow into the coil, they will induce the magnetic field. So when there is a magnetic field pass through the another coil, they will induce a voltage. Okay, so when there is a voltage, so they will induce the current also. So when there is a current, so you can charge your device. Okay, so you can see in the EMC center, EM center, there is 2 circuits of one is the producing the with the power supply, and the other is they call this what, macam wireless. So when you close the coil together, so the light will be on. Okay, the concept is similar with the wireless charger. And the third one is the motor action. Motor action. So when there is a current carrying wire in the presence of magnetic field. Okay, so when there is a current and there is available magnetic field, so the force will be induced. Okay, so the difference between 1 and 2 is only one will be provided. One will be there. For example, only current or only magnetic field. Okay, and the motor action, both of them are there, the current and also the magnetic field. Okay, the current from the wire power supply, and the magnetic field maybe can be from the magnet, from the permanent magnet. Okay, so yeah, motor, DC motor, I believe you see the inside, what inside. So the force will be induced. So later on we will cover the other three. Okay, so and then the principle 4, which is the general action. So a moving wire, so moving wire in the presence of a magnetic field. Okay, has a voltage induced. So when there is a magnetic field, you move the wire, so the voltage will be induced. Okay, so this is I think the basic general principle. Okay, so where the direction of the lines of force around a conductor is readily determined by a Ampere right hand grip rules. Okay, so just a hand grip. Okay, right hand rule lah. Okay, senang nak cakap right hand grip rule. So because other some of them they use a right hand rule, so like this. Okay, this one is a grip. We can say is right hand grip rule. So current is to the thumb. Okay, and the other magnetic field is the other fingers. So you just on the wire grip, so the wire will flow to the thumb direction. Okay, so this is the symbol of the current entering or current leaving. So this one is leaving, and this one is entering. So kalau you want to imagine, you can imagine the dart. When you throw the dart, you look from the behind. So that go through into the page. So the belakang kan, dia punya belakang tu ada X. Okay, so this is like a come out. That the dart tips. Okay, it's very just like macam needle kan. So needle tu ibarat ada needle yang keluar. Okay, so into the page or leaving the page. Okay, so this is magnetic for the earth. So the magnetic flux line will come out from the knots. Okay, come out from the knots and entering to the south. Okay, and this one, if you can see here, is is quite different. So this is the north pole, and this is the south pole. Okay, so S, and this is the north. So inside is different. Okay, this is south and this is north. Okay, because they come out from the north, but they call it as a south pole because of when you use a compass. Okay, you put a compass over here, for sure they will show you like this. So north is over there, so over here is north pole, and this is the north pole, the south pole. Okay, I think this is a basic. Okay, so this is very important. So this one we will use for the, I can say, for the whole course. Right hand and also the left hand Fleming rules. Okay, so if you want to remember, I think the best use FBI. Wait. Yeah, it lag already. Okay, FBI. Okay, so ingat sentiasa ingat FBI. So F starting from our thumb. Okay, FBI. So I is the current, B is the magnetic field. So same goes to the left hand rule. So the left hand rule is for motor movement, for the motor action, and the right hand rule is for the generator action. Okay, so the production of the magnetic field. Okay, so this is how to generate. Okay, so if you can see the figure here, so this figure is like a generator. It's like a transformer. It's like a transformer. So actually, it's come from the Mps Law. So if you go through the Mps Law, we can see the integration. The integration of magnetic field intensity. So H is the magnetic field intensity with respect to the dl. Dl is the differential element of path length. Okay, so when we integrate the magnetic field intensity, so we will get the I net, the total, I can say the total current, the total current. Okay, so what do you understand with this, the integration of dl? Anyone can answer it? Jawab lah. So integration is like a summation. It's like a summation. Okay. So for example, we have this is L1, this is L2, this is L3, and this is L4. So when we use the integration, we assume the H is in the L1 is constant, so they will become they will become L1 plus L2 plus H2. H2 H1 H2 H3 3 plus L4. L4. So this is similar to the integration of H dl. Okay, which means that the magnetic field intensity is not constant for the all length. Okay, so if constant for all length, so they will become only L total. Okay, so this is will be I think this is the simplified version. Okay, so essentially all the magnetic field produced by the current will remain inside the core. Okay, so when the current go through carrying flow to the wire, so they will induce the magnetic field intensity, and also the flux. Okay, so yeah, we assume that all magnetic field produced, the produced magnetic field will remain inside the core. Okay, we assume that all magnetic field produced will remain inside the core. So macam tadi kan ada line kan, ada line produce. So dia macam ada turn over here, so they still remain. So they not macam dia takkan keluar lah, dia takkan keluar sini, takkan keluar. Assume not go through. So they remain inside. Okay, by assumption. So that the path of integration in Ampere's law is mean path length. So you can see here mean path length, they will take only the center. Okay, every calculation will calculate using the center of the core. Okay. Okay, so that's called mean path length, the LC. So the current passing within the path of integration INET is then become NI. Okay, so this one. So yeah, for example, if only one coil, okay, this enter, cuba nak lukis ni. Boleh imagine. So only one coil, so this is the INET . So NI, so I is 1, so equal to I. So the more turns, they will induce more magnetic field. Okay, and the current will be more. Okay, so actually the current is still the same, but multiple with the number of n, and it will produce more magnetic field. Okay, compared to the less number of turns. Okay, so Ni become INET become Ni. Okay, so since the coil of the wire cuts the path of integration n times while the carrying I, so Mps Law become like this. So as I mentioned before, so the H over here we assume constant. Okay, we assume constant. So H LC. Don't worry, because after this also we will use this equation. Okay, we will not use the integration term. We will not use that. So we assume the constant. We assume that we make an assumption. Make an assumption that the H is constant. So the equation become HLC equal to Ni. Okay, so this is the we rearrange. Okay, we get the magnetic field intensity vector. Okay, so where Ni is called magnetomotive force. Okay, or MMF. Okay, magnetomotive force. Okay, later on we will look at the comparison between the electronic circuit and also the magnetic circuit. So the H is the sense of measure, a measure of the effort. Okay, okay, the just sense of the effort that the current is putting into the establishment of the magnetic field. So it's not the magnetic field magnitude, but it's the effort. How much effort? Okay, what is the effort? Okay, so the strength of the magnetic flux produced in the core is also depend on the material. Okay, so therefore there is a material study. So if you look at the mechanical department, we can see there is a material department of material. Okay, so they conduct a material study to look what is the best material for the current to flow, the conductive material. Okay, of course there is a difference between the iron, the steel, the alloy. Okay, there is a individual constant. So this is so what we can see from here, magnetic flux. Okay, magnetic flux. To produce a magnetic flux, they will look at the effort and also depend on the material. Okay, magnetic flux depend to the effort and also depend to the material of the core. So the equation become like this. So B is equal to the material parameter times with the effort. Okay, the intensity, the magnetic field intensity. Okay, so this is the relationship, magnetic field H and the resulting magnetic flux density. Okay, so B they call it as a magnetic flux density. Okay, H is the magnetic field intensity. Okay, so the mu, this is called as a mu. So mu is the magnetic permeability of the material. So the unit is Henry per meter, and the magnetic field intensity is ampere turn per meter. And B or the magnetic flux density is a Weber over meter square or Tesla. Okay, so mu also they will have another ratio. They call it as they call it as the permeability of any other material compared to the permeability of the free space. So we can compare, okay, compare with the material itself, for example the steel, okay, and also the free space. We want to compare. So we call it as the relative permeability, so mu r, okay. So where the magnetic permeability of material divide with the permeability of the free space. Okay, the free space is constant. Okay, the value of the permeability in the space is constant. Okay, so for example, when we do calculation, you get that mu r of for example steel is equal to 2000. Okay, what does it mean? So it means that the current or the magnetic flux can flow 2000 times or more flux. Okay, 2000 more flux. Okay, 2000 more flux compared to the free space. Okay, understand? Boleh faham?
Yes.
Okay. Okay. So please don't get confused with the terms. Okay. So the term is important because we have mu r, and we also mu 0. So mu 0 is free space magnetic permeability. Okay, and this is the relative permeability, and this is the magnetic permeability of the material. Okay, so material ni free space. Okay, free space, and this is the relative, and this is the material. Okay, so don't get confused. So I afraid student confused with the term. Sometimes we give you the relative permeability. So relative permeability cannot be used directly. So you need to times with the free space. Free space punya ni lah, permeability. Okay, so note that the H is representing the effort exerted by the current to establish a magnetic field, where mu representing the relative ease of establishing a magnetic field in a given material. For example, dia macam ada satu they call it what, catalytic apa, alamak dia macam apa nama ni, saya lupa catalytic macam apa, catalyst something like that dia macam memudahkan, so make the things ease to flow the magnetic field magnetic flux. Okay, so we have this equation, and we have also the Mps law or the H index I, or we have also this intensity vector equation. So with this equation and also with this equation, okay, plus with this equation, we can produce another equation. Okay, so we just replace the H over here. So this is the H, this is H, okay, this is H. Okay, we just replace here. So sometime in the equation they give you LC and this one, and you need to find the current. Okay, so that's how we play with the question. So now the total flux. The total flux is different from the magnetic flux density. So this is the total flux, or at least they call it as a flux or magnetic flux. Okay, so B is magnetic flux density. Okay, don't get confused. So magnetic flux is equal to integration of the B with respect to the area. Okay, as I mentioned before, how integration operates. So I really hope that you can try to relate with this one. So B times with the area A, and then area B, area 1, area 2, area 3. Okay, so how they make it okay, by using the this equation and integration. Okay, if the B is constant, so then they become, if B is constant, it become B. Okay, if constant. Okay, if the density vector is perpendicular to a plane and if the flux density is constant throughout the area, so the flux become BA. And then we replace again with the given equation. Okay, we just replace and then we get the equation. So later on you can play around with the equation. Okay, so now is the comparison between the magnetic circuit and also the magnetic circuit and also the electric circuit. Okay, this is the analogy, the comparison to make more or easy to understand. Okay, so throughout the course, so we will anything, for example, motor circuit, motor or transformer or generator, we will transform the magnetic circuit to the electric circuit, or from the mechanical like this, mechanical things like this, from the mechanical display like this, so we will transform to the magnetic circuit. Okay, so that's why, to make it easy understand, we compare with the electric circuit. Okay, so for example, in electric circuit we have the power supply, which is the voltage. Okay, power supply, and then we have a current flow, and then we have also the resistor. Okay, and then in the magnetic circuit, we will have the magnetomotive force. Okay, magnetomotive force is equal to Ni. So it's like F, something like that. And then it's equal to Ni. This is the magnetomotive force. Okay, if you compare with the electric circuit, they become like a power supply. Okay, and then the flow in the circuit is the flux. Okay, it's not B, it's not H, but it's flux. Okay, the current is similar to the current. Okay, and the resistance over here is a resistor. They call it as a resistance, and at the magnetic circuit they call it as a reluctance. Okay, so reluctance. So the unit is ampere turn per Weber. So the concept of calculation is similar with the Ohm's law. Okay, where over here is like a V equal to R. Okay, V equal to IR, and this one is magnetic force equal to flux with the R. Okay, so this is the analogy, the comparison. Okay, it's like a Ohm's law. Okay, so can you imagine from here, this equation, the flux equal to BA, and then we try to expand it. We replace with the other formula for the B. We replace the B equation. Okay, and then we take out the Ni. Okay, so from here you can see the flux is equal to F equal to mu A over LC. Okay, if you compare from here, okay, so kita terbalikkan rearrange. So this one become LC mu A flux. Okay, time flux. So this is the reluctance. Okay, so it means that the reluctance inverted so you need to invert it. Okay, kita kena susun balik lah main equation so kita tak boleh lah main, we cannot just directly use the given equation without manipulate. So this one is terbalik kan lah. Dah terbalik. Oh. Okay. So the reluctance is equal to the LC divided by mu and area. Okay. So from here, just now we see the current flow, and then when there is a current flow I, so the magnetic field direction is like this, right hand rule kan. Pada right hand rule, alamak tak pandai lukis dia ni. Okay, so the flux, so this is I, and the flux is will be like this okay, this is magnetic field intensity. Okay, so over here, to know the direction of the flux, okay, we use also the right hand rule. So there is a current flow, okay, there is current flow, and then looping. Kita tengok ada looping So ni, this like we grip by using our fingers, okay, and this is the direction of flux. Okay, so whatever come out with the power supply, for example, this is, we call this a magnetic force, magnetomotive force. Okay, so whatever come out from here, the sign over here is positive. So this is the where the magnetic flux come out. Okay, so ni magnetic flux comes in. Okay, so they call negative, the sign of negative. Okay, so the calculation of the reluctance, whether in series or in parallel, is same. It is the same with the electric circuit. Okay, so don't get confused. Okay, so yeah, sometimes we have few things, we have different area. So when we have a different area, we will have a different calculation. Okay, and then if we have another example, if we have another, the air gap. Okay, air gap is another reluctance. Okay, we cannot combine. So there will be either in series or either in parallel. Okay, so the first question for today: what are the reasons for inherent inaccuracy in the magnetic flux calculation? Okay, so yeah, in the book they write, they say that the calculation of the magnetic flux, okay, by using this equation, this equation, blah blah blah, this equation and the previous equation, they mention that the accuracy is only up to, is within about 5% of the real answer. 5% only. Okay, 5%. 5% only the accuracy by using this kind of equation. Okay, so the question is why? Okay, what are the reasons for the inherent inaccuracy in the magnetic flux calculation? However, they are still using. Okay, the researcher still use this kind of calculation. Okay, this kind of equation they are still using. Okay, so interesting, 5% but still using. Okay, so yeah, the first reason is because of the why they are still using it, because not what are the reason, but why they are still using is, firstly, is because of the simplicity. The simplicity, and they say even though not accurate but still can be used. Okay, so there is a exact calculation by using the Maxwell equation. Okay, but it's too difficult. Okay, this one, even though the 5%, but they say is a they can get a satisfactory result. Okay, they satisfy the result will be they satisfy with the result. Okay, so I already create the author assessment, not the assessment, the revision. This one will be appear in the, actually it's appear already. I believe it's appear already in the author. You can see it, and the answer is in the book. Okay, the answer is already in the book. Okay, you just read. I want you all to read. Go and read. Okay, so we go to the first examples. Okay, the first example is quite easy. Okay, so a ferromagnetic has 3 sides of uniform width. So they mention already, 3 sides of uniform width. Okay, so which means this side 1, 2, 3. So this is uniform. Yeah, of course the rectangle they have 4 sides. So but they say 3 sides is uniform, means that the 3 sides is the same. How to know the side is the same? You just look at this point. Okay, you need to, there is a skill kita perlu ada skill untuk baca benda ni Kita separatekan dia like this like this. So the width of this length from here to here is, the width is 15, or you can say the height, but it's okay lah, width pun okay lah. Okay, so since the width is 15 constant for this side, so from here to here you can use the the same calculation okay, but don't stop there. We look all side first okay, this one also the same 15. So from here, why start from here? It is because of the mean path length so you need to understand so this one 30, ni calculation ni kena main. So this one 30, and this one the length is not 10 but 5, and this one is 1.5. okay, please be remember the mean path length not the total length, not the length from end to end, but the mean is at the center. Okay, so this point also, this one 30, this one 7.5, and this also 7.5. okay, this one 30, so this one also 15 the width. So this one also, this one 5. okay, so 5, 30, 7.5. so with some all together they will become L2. okay, it's okay, we
Doctor,
yes.
I have a question, doctor. Okay, that 15 cm and 10 cm, doctor say need to divide by 2, right?
Yes.
If they didn't mention or given a particular value, means we need to divide ourselves by 2. Is it right, doctor?
Yes. For example, like this, for example the 15 over here okay, for example 15 they show you from this point okay, this point up to the end. okay, so since the mean path length which is at the center, so we need to divide by 2. okay,
Doctor, if the mid length is not in the center, is slightly left or right, means they will give the value or what, doctor?
What I can say, normally they will use it at the center and just divide by 2. okay, unless there is a specific equation. okay, specific question. However, you can still understand. okay, don't worry.
Okay, doctor.
okay, for now just make it easy, and I believe it will use up to the end of the course. Just divide by 2. okay, because they just take at the center. okay, let's read the whole question first. okay, the uniform width, while the fourth side is slightly thinner. So this side is slightly thinner. So the depth of the core is 10. So why the depth is important is because to calculate the area. okay, so the number of turn of coil wrapped around the left side to 100, assuming the relative permeability of the ferromagnetic core is 2500. So it means that the magnetic flux flow 2500 more than compared to the free space. Okay, so how much flux will be produced by the 1 ampere input current? Okay, for example, the current here is 1 ampere. So what is the flux? Okay, so we have we need to use the equation. Okay, so we have a flux to Ni, and then we have this one. Am I right? So first we need to find the R equivalent. So we need to have a R equivalent equal to R1 plus R2. Okay, so what is R1, what is R2, we need to calculate first. Okay, and then we have the number of turns, we have the value of current, and we can find the flux. Okay, so that is how we calculate. Okay, and then the 300 turns, for example, yeah, they mention the 300 turns. So we need the flux. What is the flux? How much flux will be produced if the turn is 300 and the coil input is 2 ampere? Okay, so R equivalent already will be already calculated in the question A. We just change this one and magnetic force. Okay, and then we get the flux, and then calculate flux density at L1 and L2 in case B. Okay, for example, they ask you to use this one, 300 and 2 ampere. So calculate the flux density, the B. Okay, in each side. Okay, not each side, yeah, the uniform side and also this sides. Okay, the L1 and also the L2. Okay, so from here, okay, wait, I delete, erase few things. Okay, from this mechanical, I can say a mechanical diagram, we translate to the magnetic circuit, to the magnetic circuit. So what we can get is, it is like this. Okay, so please remember, so when there is a coil over here and also I can say it's a loop, a loop of core. Okay, the circuit will be like this, where there is a power supply and there is a flow of flux, and there is a two reluctance. Okay, macam two resistor, magnetic circuit. So ada power supply, like ada macam ada current flow, and then there is a resistor 1, resistor 2. So reluctance, reluctant 1 and reluctant 2. Okay, so what happened? So nanti lepas ni, after this you will see a different types of diagram. For example, maybe you will see like this. You will see like this. This is a core. Okay, and maybe like this. Okay. Okay, and maybe like this. Ada air gap. Okay, so ada air gap. Okay, ataupun like this, and then okay, so you will see many diagram after this. The basic calculation is the same. The basic calculation the same. You need to measure the area, the length, the reluctance. Okay, the figure will challenge you. Okay, first of all we need to calculate the R1. Okay, the R1 is over here. So later on you try to calculate the 45 over here. So this is 7. This is 7.5. Okay, and 30 times by multiply with this, so it become 45. So total here is 45. So 45 is in cm, but they calculate in meter. Okay, so you need to change to the meter. Okay, L1 is 0.445 meter, and then mu times with the AI, the area 1. So this is mu r, and then the free space parameter, and then the area. So the area, the depth is 10. The 10, this one, the 10 times 10. Okay, so A1 is equal to 10 cm times 10 cm. So they will become 0.01 meter square. Okay, so then you get the value of reluctance 1. Same goes to the area 2. So you sum up from here, 5, 30, 7.5, 7.5, 30, 7.5, 7.5, 30, and then 5. Okay, sum up all together will become 1.3. Okay, so the area over here, the area is the same. Area is the same, 15. So this is dia punya width, dia punya apa, lebar dia 15, and then kedalaman dia punya depth 10. So A2 is equal to 15 cm times the 10 cm. Okay, it will become 0.015 meter square. Okay, so then you get the R2. Okay, so the R total, or sometimes they call it R equivalent. R equivalent also can. Okay, R1 plus R2. Okay, just sum these two. Okay, then you get total or the equivalent. And then as I mentioned before, you just use likes and Ohm's law. Okay, like and Ohm's law, which is F equal to flux R total. So you just this one is equal to Ni. Okay, so you have 200 turns times 1 ampere. So just rearrange, then you will get the flux. Okay, so this is a Weber. Okay, so question A. Okay, so now we go to the question B. So question B, the value of R calculated already. You just change the value of Ni, MMF. Okay, so you can see here. So this is the value or the answers. Okay. Okay, so then we go to the they ask you to measure the flux density at L1. Okay, so we know that the B, not B, but the flux equal to BA. Okay, we already know that. So this is the, if you want to calculate the B1, so B1 I1. Okay, so B1 I1 is equal to B2 A2. Okay, because the flux is the same. Okay, the flux is the same. Okay, for example, current to resistor kan, dia macam like, kita nak analogi nak mudahkan pemahaman. Okay, so current flow ni resistor 1, resistor 2 kan. So current flow tu sama, tapi voltage yang berbeza kan. So ni voltage 1, ni voltage 2. Okay, same goes to here. The analogy is something like that. So the flux is the same, but the intensity is different. Okay, because there is a different area. Okay, because the changing in the area, so that's why the flux intensity is different. Okay, so area 1 pun dah ada. We have calculated, this one is calculated, area 1 is calculated, so we just divide and then we get the intensity, which is the Tesla for B1. So B1 over here for the L1, and then flux density at L2. Okay, B2, so we get the answer. Okay, so up to now can understand?
Yes.
Okay, great.
Yes, Doctor.
Okay, so this is what I mentioned, where you will see the air gap. Okay, you will see the air gap over there. Okay, the question is a ferromagnetic core with a small gap of 0.05. So this is 0.05 cm, has a mean path length. Okay, mean path length of 40 cm. So this one similar with before, which is there is only two reluctance. Okay, so we will have only two reluctance. This R1, this R2. Okay, or this is, for example, this is air gap, air gap, and this is the SC. Okay, the cross section area, relative permeability, and coil number of this one. So this is area. So area calculated already. So they want to make you easy understand. So A core is 12 cm square, 4000 coil, relative permeability, and 400 coil turn. If the flinging of the air gap increase the effective cross section area of the air gap by 5%. So maksudnya the area of the air gap increase 5%. Okay, the flinging effect like this. Ni for example I ambil yang kat sini. So dia like this. So flinging effect tu bila ada flux, so flux yang go through macam ni kan. So dia akan ada macam flinging effect, macam boom sikit. Okay, so it assume the area increase by 5%. Okay, so this AC is equal to 12 cm. So area of air gap, I can say AG is equal to 1.05 AC. Okay, more 5%, or the increase 5%. So you need to read carefully the question. So either increase or decrease. Okay, so this is how you calculate. So when they say increase, so you need to top up another 5%. So to make it easy, we use the ratio. So 1.05. Okay, so why it is because 105 divided by macam tu lah lebih kurang. Tapi this is the most easy calculation. So you calculate until you dapat berapa ni. Okay, they ask you to find what? Find the total reluctance. Okay, total reluctance, the R equivalent, or R total. So is R1 plus R2. Okay, and then the current required to produce a flux density. So kita ingat so flux density is specific at that area. I can say it's, or length. If they use if they ask you to calculate the flux density at the air gap, so you need to use the area of the air gap. If they want to ask about the flux density at the mean path length or the core, so you need to use the core area. Okay, so let's start. So RC is R core, the R core, the core reluctance of core. So 40 cm already given. So convert to the meter, and then 4000 mu R, and then mu naught, and then the area. So everything is given here. Okay, you can get the RC, and then the air gap. So the air gap is around 0.05 cm, convert to meter, and the mu R is 1. Okay, the mu R is 1 because it's the space, so the same with the mu naught. Okay, the relative is 1. Okay, and then this is the calculation. Increase, we need to increase the area 0.012 times 1.05. Then you get the reluctance, and then you sum up together. R total is RC plus R air gap. So then they ask for a solution A for the reluctance, and to calculate the current required for to apply to produce 0.5 Tesla magnetic density. So we just use this one. So please remember we use the air gap punya area. So 0.5. So yeah, of course, when they ask you the current required to produce a flux density of 0.5 Tesla in air gap, so which means that this is the B air gap also. Okay, so B air gap and B in the core is different. Okay, the same is the flux. Okay, the flux is the same. Okay, this is the same with the core. Okay, so B is a B air gap times with the area of air gap, and then you get the flux, and then use the, I can say it's like Ohm's law, then you get the current. So by providing this current, this value, so you will produce 0.63 flux. Okay, they are the million. Okay, example 3. I want to cut short. Wait. Mana ni? So I skip I go through the magnetic field ni untuk example 3. Okay. So they say there's a DC motor, ada main path length 50 cm, the area, okay, and then the main path length of the rotor is 5 cm, okay, and then the area is assumed to be 12 cm square, and each air gap, so the first air gap is over here, the first air gap, and this is the second air gap. Okay, the gap is 0.05, and the cross section area of each air gap, okay, is 14 cm. Okay, so they given already. They given all the information already. So the iron core has a relative permeability 2000 with 200 number of turns. If the current in the wire is set up to 1 ampere, find the resulting flux density in the air gap. Okay, so I think better we start from the magnetic circuit. So we have the MMF, and then we have the reluctance of the core, RC. Okay, and then we have reluctance of R1. Okay, and then we have R, and then we have air gap 2. Okay, so we have total of 4 reluctance. So our core, air gap 1 over here, and then over here the rotor, and then the air gap, the second air gap. Okay, so the air gap they combine already. The air gap is combined already. Okay, so they calculate 1. Okay, they calculate 1 air gap, the same parameter, and then the times 2. Okay, the times 2 over here. Okay, calculate the reluctance, sum up together, you get the RT, and then they ask for dah stop. Okay, dah stop. Okay, find the resulting flux density in the air gap. So mean the B. Okay, so yeah, to find B, you need to have the flux, and then you need to have the R total, current. Okay, so once you get the flux, Okay, once you get the flux, you use the air gap punya area. Okay, then you will get the value. Okay, so I just I speed up about this. Okay, so this is the magnetic behavior of ferromagnetic materials. Okay, the permeability, I think I touched it before. Permeability of ferromagnetic material is very high, up to 6,000 times. Depend on the material. Okay, 6,000 times compared to the free space. Okay, in the example, the permeability was assumed to be constant regardless of the magnetic force applied to the material. So normally they assumed to be constant. Although the permeability is constant in free space, this most certainly is not true for iron and other the ferromagnetic material. Ferromagnetic material ni macam dia boleh mengalirkan flux lah. Okay. Okay, so kita start from here. Kita tengok pada sini. Kita buat test. Okay, we try to do a test. For example, there is a coil. Okay, the coil, and then we apply a DC current. We apply a DC current. Okay, where this is Ni. So Ni, so start from current. Start from zero. So this is start from zero. So then we increase. So when we increase, they will rapidly increase the flux. Okay, so the flux I can say is quite linear. Dia macam linear lah kat sini. Linear. And then at some point they will saturated. Okay, that is saturated. So from the equation before, we can see that the F, okay, the F or the Ni is perpendicular. They call it astaghfirullahaladzim. They call it what? Proportional. Proportional to the H. Okay, proportional to the H. Okay, and then the flux is proportional to the B. Okay. So therefore, when we convert the unit, okay, so we can see the same here. Okay, the same effect. Okay, not the similar but the same. Same effect. So they will increase, and at some point they will saturated. Okay, so this is as a knee. Okay, so mostly they will operate somewhere here. They will be operate around this part only. Okay, they will avoid this point. Okay, because kalau you inject more current, so with more current, and then they will they will have a issue, temperature issue. Okay, so this is comparison between steel Y and steel X. Okay, so of course every steel or material will have a different characteristic. So this is energy losses in the ferromagnetic core. So instead of applying DC to the winding, what will happen when AC current is applied? So this AC current apply, and they will affect. For example here, starting from here. So starting from here, okay, for example like over here to here. So bila dia naik, okay, they can go through. They will start from zero. They start from zero. Okay, the path is AB. Okay, so when go back to zero, so they will not flow to the same path. Okay, they will go back to the different path. Okay, so they will go through a different path. Okay, they will from here. This is from here to here. The flow is A, B, C. Okay, and then so this is current increase. Current increase in the negative side. So they will go back to the highest in the negative side, and then when they go back, they will not go to the center. They will go to the different center, other path. Okay, so sampai habis. Okay, they not go back to the zero. Okay, so this is called a hysteresis loop. Okay, the current increase from 0, okay, A to B, and then as current decrease, they become BCD. Current increase again, they go to the DEB. They will not go to the center again. So this is called as a residual flux. Okay, so this amount of flux not only depend on the amount of current applied to the winding, but also the previous history. So seolah-olah macam dia dah ada they store few flux over there. So this is what magnet happen . So kenapa ada magnet boleh tarik, okay, so magnet can contact okay, to each other because of this phenomena because the flux is stored over there. So amount of flux is not only depend on the amount of the current applied to the winding, but also on the previous history of the flux in the core. This is called a hysteresis. Okay, so again, the second question of today's lesson is why does hysteresis occur? So, okay, so for today's lesson, I will stop until here. Okay, I will stop until here, but I will share the video. I will share the remaining 1.4 to the I think up to 1.6. I will share the video. So you can study throughout the weeks. Okay, so we also have a time to 5 p.m. Okay, I just go through Faraday's law. So you ada ni magnet. Okay, when this magnet produce a magnetic flux. So when you cut through the coil, they will induce a voltage. Okay, so the more the turns, okay, the coil turns, the more the inducer. Okay, so why negative sign? It is because of the opposed direction. So this is the sign over here is come from the Lenz's law. Lenz's law. Okay, so Lenz's law state direction. Betul bit up. Okay, ni yang senang. So ni ada turn. Okay, and then you supply magnetic flux. Okay, you supply magnetic flux, and then magnetic flux will be induced, or voltage will be induced, and then the magnetic flux also will be induced. So where the direction of magnetic flux will be induced? In this direction. Okay, oppose the supply, oppose the direction of the flux. Okay, and then this one you cannot use the right hand rule. Okay, I think can. I think you can use the right hand rule. So to the direction. But the induced, since this coil is induced coil, not the supply coil, supply coil, but the current flow through the induced operation. So the voltage will be like this. So this become like a power supply or a battery. Okay, so current flow like this. Okay, so tadi kalau kita tengok dia masuk dalam coil kan, terbalik. Tadi kita tengok dia macam ni, dia masuk dalam coil, betul tak? Masuk coil kan, so sini positif. So now is induced. Once induced, the direction is terbalik . Okay, so sepatutnya dia ni lah. Okay, tapi we don't want to use the sign in the equation. Okay, we don't want to use the sign equation over here, so we just directly put positive over here. Mana gambar ni? Okay, so we put already the sign, we terbalikkan dia lah. Okay, so ni magnet lah, nanti you boleh tengok lah ni. Okay, dia maksudnya sama lah dengan ni. Okay, ini I think you dalam video ada penerangan. Okay, in the video there is a explanation. So I just go through. So is the eddy current, so also in the auto. Okay, so ni motor action. So you use the left hand rule. Okay. So when you see the equation like this, so this mean is a cross product. So from the mathematics, you can Google it. So what happen when L cross B? So there will be magnitude of L, magnitude of B times with sin theta. Okay. Okay. I think dah ada video tu lah. Okay, so same goes to here, cross product and also dot product. Okay, so semua dah ada penerangan dia. Example pun ada. So later on I will show you the video. Okay, any question up to now? Hello?
Not yet.
Not yet. Okay, so please ask me if you have any question or you don't understand, please ask me. And I already create a quiz for second week study. Okay, for the second week, I create the quiz, and you can answer it throughout the weeks. Okay, you can ask me for the quiz. Okay, you can ask me if you don't answer, but I will not give you the answer lah, but I will help you to answer it. Okay. I can say it's a free marks. You can find the answer somewhere, but I don't want you just copy. I want you to understand it. Okay, this is very important. Okay. Oh, ada satu benda yang lagi important. Lupa saya. Okay. Terima kasih. Jangan keluar dulu. Okay. So ingat tadi. So kita ada gambar macam ni kan. Tak lah. Nanti you confuse. Sekejap Okay, so you ada ni, ada ni, ada ni. And then kita ada coil. Okay. So kita ada I, positive, negative, and this ada. Okay, so so from here, okay, from there when you convert to the electric circuit, okay, so you will get like this, okay. This one, okay. So what happened when you have this one? Okay, when you have one, do, okay. So you need to make it like this first. Okay, you need to make it like this first. Okay, how? You can see here, the part with the coil, you ignore it first. Okay, you ignore it first. Okay, but the other part, you can see that this part, okay, this part, left and right, is a parallel. Okay, it's a parallel. Okay, so you when you convert like this, it will become only where they will become. So this is the pattern of the center. I can say this is center, center, and this is the parallel, parallel wheel. Okay, so not everything. You don't need to calculate parallel everything including the center. Don't that. Okay, just do the left and right. So then you will become like this first. Okay, for example, you assume lah the right and left they become ada air gap ke apa benda kan. So air gap. So this is parallel dengan L. Okay, so ni of course dia dah ada core punya path length kan. Dia ada dia punya path length, dia ada reluctance. It will be like this okay. So the others you just make it series in series. Boleh faham tak ini? Can you understand?
Yes.
Okay, good. I afraid student will do only like this. Okay, I afraid student will do this only. Okay, where is RC L parallel with R. Okay, RL, RR, RL lah. Okay, dia bukan parallel semua. Don't parallel to everything. Okay, make sure when there's a coil, okay, look at the other. The other is what? Series or parallel. Okay, so kalau others is series, no need to do a parallel things. Okay, so I think that's it. Okay, so we rest first and then I will share the video. Is it okay?
Okay, doctor.
Okay.
So kalau tak ada apa-apa lagi, I think I will stop here. I will stop the lesson today. Using the Google Meet. I will stop here and we will continue in the I will share the video later. Okay, that's it from me. Thank you, and don't forget to do the revision and don't forget to do the quiz. Okay, thank you. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.